We're going to continue today's lecture talking about PMFs and PDFs. So let's start with a real quick review of the concepts last time that we went over. And we had this idea for random variables where if I had a random variable, say RV, let's call it capital X, and if this random variable was discrete, we could define what was called the probability mass function, or PMF for short. And what the PMF told us is if we say plot the values in our support, that is the places where the probability of our random variable x being there is non-zero, we could plot our PMF, typically denoted little f, against our values on our real line here. And we could make a little stick plot so that the height of the stick at each point corresponds to the probability of that our random variable ends up at this spot. So if my point here is little x, then the height here is f of little x, which is the probability that my random variable capital X lands at little x. So the probability that capital X is equal to little x. So this worked for a discrete random variable because discrete random variables take on some discrete set of points. That is the places where my random variable x can land with non-zero probability is some discrete set. Could be infinite, could be finite, but it must be at least countable. And so I'm going to have a kind of discrete set of kind of sticks here. And I have a non-zero probability of landing at various points in my support. The function, little f, is defined for all possible real numbers. But if I look at a point, say here, where I'm not in my support, where the probability that my random variable ends up there is zero, it's just going to be zero. So we're basically ignoring those in this plot, but you can think of them as lying on this x-axis. So everywhere that's not kind of that doesn't have kind of a stick is zero. We then talked about continuous random variables. And for continuous random variables, we had an analogous concept called the PDF, or probability density function. And the problem was that if I picked any point, so if I looked at any little x, that's a number, and I ask, what's the probability that my random variable is exactly equal to that little x value? This is zero, always. The difference is that in the discrete case, I have a kind of discrete set of points in my support where I can have non-zero probability. In the continuous case, I have a whole continuum of values that I can take on with that I can possibly end up at. Kind of paradoxically, this means that since I can take on any values in some continuum, I can't have a non-zero probability of ending up at any of them. Otherwise, I'd end up with way too much probability overall. I wouldn't end up with my probabilities kind of adding up to 1. So I think a plot here is informative, and we again use kind of analogous notation where little f denotes my PDF, and I can plot little f against my real line. And instead of being this kind of stick plot where I have it's non-zero for a discrete number of points, now we have some kind of smooth continuous function. And the value of this function, so if this is some value, let's say little x, then the value f of little x here is what we call the density of my random variable at this little x value. We should note here, this is not that my PDF does not describe the probability that my random variable ends up there. The reason is the probability that my random variable ends up exactly at any individual point here, in the continuous case, is always 0. So it is not describing the probability of ending up at each point. It is describing the density. But in many ways, that density kind of behaves as if it were this probability. So in many cases, it's kind of a distinction without too much content, but there are cases where we really need to understand that in discrete case, we can end up with a non-zero probability at some individual point. In the continuous case, I have this whole continuum of values I could land at. And we'll kind of see and maybe argue later in the lecture that you couldn't have a non-zero probability of being at any individual point, because then if I kind of summed up or integrated all of my probabilities, I'd end up with way too much probability. I'd end up with probabilities over 1. So kind of paradoxically, if I ask what's the probability my continuous random variable is at any individual point little x, that's always 0. Nonetheless, I could choose some interval, and I could ask what the probability is, say, for being in some interval, and that can be non-zero. So we can actually get non-zero probabilities out of this density function, and that's what we're going to end up doing. But because it kind of is spread out across the whole whole continuum of values, the probability of being at any individual point is going to be 0. And we'll expand on that later. Okay. So we had this other fact that we kind of ended with, and that is the CDF, recall, is a function for either discrete or continuous where capital F, which I used to denote my CDF, is the probability that my random variable is less than or equal to some value little x. Okay. And in the continuous case, we said that my PDF, little fx, is actually the derivative of my CDF. So this is kind of fundamental relationship between the PDF and the CDF in both the discrete, but in the continuous case is really nice because now we're starting to use the rules of calculus. And alternatively, and in fact, the way we kind of define the PDF in the continuous case is that the CDF f, capital F at little x, is the integral from negative infinity to little x, and we'll say of f of t dt. The variable t is a dummy variable. You replace it with y, replace it with z, doesn't matter. I didn't want to use x because I didn't want to clash with the argument of this function, which is different. So this is this kind of fundamental relationship between the PDF and the CDF in the continuous case. We can see some of the properties that we had claimed generally are true of the CDF. In light of this relationship, they make sense. So some properties for continuous CTS random variables. Okay. So for all random variables, we had made this claim that if I wanted to look at the probability that my random variable was in some interval a to b, and we're going to be very specific in general, that is x is less than or equal to b, but greater than a. And those that greater than and that less than or equal to have to be what they are. You can't have a less than or equal to x or something like that. In this case, we had made this argument. If you go back and look at the argument for why it is true that this is equal to f of b minus f of a. So that relates probability that x is in some interval to the CDF. Now, if we're talking about continuous random variables, we have a relationship between the CDF and the PDF. And so I can, if I want, I can write out what the CDF is, right? So CDF at b is going to be the integral from negative infinity to b of f of t dt. And then I'll subtract off the CDF at a is the integral from negative infinity to a of the PDF, little f of t, at dt. And using my calculus 1 knowledge, I can combine these, actually. This is the integral from a to b of f of t dt. So, interestingly, if I want to, so if I have my kind of number line here, it's my real numbers, and I have some interval, say a to b, and my, PDF maybe looks like that, kind of in this interval, all I have to do to get my probability of being in this interval is integrate probability that a less than x less than or equal to b is the integral over this interval, a to b f of t dt. And for discrete random variables, it really mattered. Again, it mattered that this is less than and that this is less than or equal to. The reason being is that you have a non-zero probability of being at b or being at a. So you have to be very careful about it. Do you include a or do you not include a? We said, though, that for continuous random variables, the probability that x is exactly equal to a, or the probability that x is exactly equal to b, is 0. So we've made this claim. We'll discuss it a little more in a second, but the probability that we're exactly at a or exactly at b is 0. And so it doesn't actually matter as much if we include this lower interval, if we don't include, if we include b or not include a. So in fact, the probability that, say, x is bigger than a and less than or equal to b, we can actually play around with as much as we want. We could change this to a less than or equal to. We could kind of change any of the less thans to less than or equal to. We could change the second one to a less than. We could make them both less thans. This is true for continuous only. And the reason being is that I can include a or include b or not include a or not include b with impunity because the probability that I'm at a or b is 0. For a continuous random variable, the probability I'm at an individual point is 0. The probability I'm at in some interval may or may not be 0, but I can kind of include a or not include b, etc. All that's going to do is add or subtract 0 to my answer. Doesn't change my answer. I don't actually really care. This is kind of part of a more general rule, which I've hinted at. Now, recall that for discrete, if I wanted to calculate the probability that my random variable is in some set A, so here, let's say A is some subset of the real line, okay? Could be an interval, like we had up here. Maybe it's not. Maybe it's a more complicated subset of the real line. Now, when it's probability that x is between -1 and 2 and 7 and 8, right? That's an allowable A. Something like that, right? For discrete, if I wanted to calculate the probability that x is an A, what I did is I summed over the points in A, I sum my PMF. So here, little f is my PMF because I have a discrete random variable. In the continuous case, and we'll see this quite often, I can make an analogous claim. If I want to calculate the probability that my random variable lies in some set, doesn't have to be interval, just some collections of real points, instead of doing a sum, I'm talking about continuous things now. So I'm just going to integrate over the set A, and let's say f of t dt. Just use our dummy variable t. And this is kind of the analogous statement. And so we saw that we can look at some examples. For example, if I wanted to calculate the probability that my random variable was between negative infinity and, let's say, little x, that's a set of the real line. This would be the integral, let's say negative infinity to little x, f of t dt. Of course, we don't typically write integrals that way. We'd write this as the integral from negative infinity to x, f of t dt. And of course, this is just, well, let's do two steps. This is the probability that x is less than or equal to little x, which we call CDF, right? And we had already made this claim that there's this relationship, but it's a more general rule. Example, if I want to calculate the probability that x is in the interval, doesn't have to be an interval, let's say, but let's say I want to calculate the probability that x is in the interval 2 to 3, maybe we exclude 2, include 3. It doesn't really matter for continuous because you can kind of throw out a countable number of points out of any set, and it doesn't really affect the probability. This would just be the integral 2 to 3 f of t dt. Now here we should be careful. This little f here is the density function, the PDF, right? So the picture, of course, is that I have my PDF against the argument, and maybe my PDF, let's say, is green, looks like that, some function. Talk about exactly what kind of functions they are. And okay, so if I wanted to calculate, maybe I have some set, and let's say it's that my set A is here. How do I calculate the probability that x is an A? All I'm going to do is integrate my PDF over A, which we, of course, we know is just finding the area under this PDF. So this area is the probability that my random variable is an A. So let's again revisit my last kind of abstract example before we get on to some concrete examples, is that what if my set A has a single point? So let's say I want to calculate the probability that x is in the set 2. Of course, we wouldn't really write it that way. That's a weird way to write it. What you'd rather do is say probability x is 2. Okay? But in any case, according to our rule, this is the integral over integral of our PDF over the set 2. So it's the integral from 2 to 2. 0. Right? And I can play that game with any number, any set 2. In fact, I can play that game with any countable set, and that integral is going to be 0. That's a fact from analysis, but certainly you believe if I have any individual point here, 2, 3, 7, 1.5, pi, I'm integrating over an infinitesimally, right? So what's the picture? The picture here, if I look at f of t against t, here's maybe my PDF looks like that. Here is my infinitesimally small, right, set, and I'm going to integrate, and I can say, okay, what's the area in that slice? Doesn't matter what my density function is. It's an infinitely narrow slice. It has 0 width. And so the integral, of course, the area there is 0. And so my probability, according to my rule, is 0. So you see that this is why we cannot interpret this thing, this PDF, as the probability of being at the point. Because the probability is kind of the area under the PDF at that point. That's the correct way to calculate it. And if I have just one little point, then the area under that point, 0. So the density function is not quite, you still kind of use it in similar ways as the PMF, but it is not telling you the probability of being at some point. If I have some set and I integrate, say, over a set A, it does tell me that the area under it is the probability of being in A. It's kind of like if I go back to my discrete case and I sum up, what do? I sum up the values of the sticks. If I want, to calculate the probability of being in that set, I'd sum up the value of the two sticks. But now we're kind of integrating or looking at the area under that. So if my set is big enough that has kind of a non-zero area, good. My probability of being in that set is non-zero. But if my thing is so small that the area is 0, my probability of being there is 0. Yet my function, this thing is still non-zero at this point. This has this function, this f of t at 2. F of 2 is greater than 0, but probability that x is equal to 2 is 0. So the density function kind of tries to play the continuous role of the mass function, but it's not quite as nice in some ways. It's nicer in other ways. Okay, let's look at some examples. Let's do a bunch of examples today. I think that's a useful thing to do. So example, I'm going to give you a CDF, f of, well, let's say x. So this is my CDF. I'm always going to use capital F for the CDF and little f for the PMF or PDF, depending on context. And I think we've seen this CDF before in the previous example. It's 1 over 1 plus e to the negative x. We showed previously this is a valid CDF. And I could ask you, what is the associated PDF? Okay. First of all, the CDF is a CDF of a continuous random variable. We know that because it's a continuous function. So by definition, the CDF is continuous, therefore the random variable is a continuous random variable. So it is continuous random variable, it will have a PDF, a probability density function. And our fundamental relationship is that the PDF, f of x, is df dx. Right? It's the derivative of the CDF. And in this case, that gives us, well, you can do it the math. I'll let you do the Calc 1 problem there. That gives us e to the negative x over 1 plus e to the negative x squared. So that is a kind of quotient rule there. So pretty straightforward. That's the relationship between the CDF and the PDF derivative. I could ask the question the reverse way. I could have given you the PDF, and I could ask for the CDF. How do you get it? Well, you integrate in a certain way the PDF. You integrate from negative infinity to little x of the PDF, and that will give you the CDF. So check, a good check to do at home is that if I want f of x, I can integrate negative infinity to x of my PDF. So I'm not going to do it, but check at home. It works. That may actually be a really hard problem. Let's just say fact. Not sure, how hard is that integral? That's probably a pretty hard integral. So maybe that's too hard of an example to give. Okay. Let's look at an example where we can do it. So here's an example where we can go the other direction. Okay. So along the way, I'm gonna be introducing a kind of a collection of random variables that we're gonna learn about. And they're gonna have names. We're gonna learn this pantheon of different random variables. So I think we've introduced like a couple discrete cases. This kind of the most simple continuous random variable is called the continuous uniform distribution. And we're saying distribution as in how the probability is distributed over the space. And in parentheses, I should say this is going to be on the unit interval 0 to 1. Okay. And this is denoted, our notation for this is that our random variable x, oops, that's squiggle, read as distributed as, so x is distributed as u for uniform and the interval 0 to 1. What is it? What do we mean say that a random variable has a continuous uniform distribution? This means that the PDF f of x has the following form. It's going to be 1 if my little x is between 0 and 1 and 0 otherwise. So typically we don't write it as case-wise. Sometimes we do, but oftentimes people leave off the second case. So often people will just write it is equal to 1 for 0 less than x less than 1. And it's implied that it is 0 everywhere else. So you'll see that all the time where people, this of course is called the support. And so what people will do when they define the PDF of a random variable is they'll define it just for the places it's non-zero. It is assumed it is 0 everywhere else. So if you see something like, oh, f of x is 1 for x in this interval, well, you can ask yourself, well, what is it outside the interval? It's 0. It's just assumed to be 0. And that's just kind of notation, kind of parlance of statisticians. Okay, so let's look at a graph of this thing, right? So I'm going to graph f of x against x. I have my unit interval 0 to 1. In my unit interval, it takes on a value of 1. And outside my interval, it takes on the value of 0. So it's a real simple picture. And it's uniform. That is, the density, the PDF, is uniform over the interval. It is uniformly distributed. It has the same density over the whole interval. Okay. Question. What is the CDF of x? So I gave you, could be a homework problem or an exam problem, I gave you the PDF, and the question is, how do I get the CDF, the cumulative distribution function? So the fundamental relationship we know is that f of x, so this is f of little x, so f of some number, is the integral negative infinity to x of my PDF. Now, this integral I'm going to break into a couple cases depending on if it's less than 0. So I can basically break into 3 cases. 3 cases being, is my little x here less than 0? So it's this argument here. Less than 0 is between 0 and 1, or is it bigger than 1? So I'm going to break this into 3 cases. 1 is that little x is less than or equal to 0. 2 is that it's in this unit interval, 0 to 1. And 3 is that it is bigger than or equal to 1. Now you notice that my cases overlap. Doesn't really matter too much for continuous random variables, and you can be kind of sloppy with the edges because the probability of being at exactly 0 is 0. It's true of any number, so you can kind of be a little bit sloppy with exactly how you define this thing. Okay. But other than that, I just have to evaluate this integral for my 3 cases. So let's do that. In case 1, integral negative infinity to x f of t dt, and this case is that, so this is 1, this is 2, and this is going to be case 3, if x is less than 0. So let's go back up to here. If x is less than 0, for instance, we're here, we're integrating the function all the way from negative infinity up to this point. Well, it's just 0 everywhere. So the integral is going to be correspondingly 0. So in this case, the integral is 0 because this thing is 0 on that entire interval. F of t is 0 everywhere less than 0. So the integral of 0 on any interval is 0. So we're going to get 0. Kind of boring case. Case 2, integral negative infinity to x f of t dt. Now, in this case, our little x, a little argument here, is between 0 and 1. So looking at some value here. Now we can ignore everything less than 0 because that has no contribution to my integral. There's no contribution in area. But for some little x here, I'm going to have some positive area contribution. And that area is going to be, well, the length is x on one side and 1 on the other side, right? So another way of thinking about this is that it's my integral of 0 to x of 1 dt, because, oops, sorry, integral from 0 to x of 1 dt. I can ignore everything less than 0, has no contribution. And between 0 and 1, my f of t is just 1, so I'm just integrating that. That just gives me x. Very simple integral. There you go. And then the third case here, integral negative infinity x, f of t dt. Again, I can ignore everything outside of 0 to 1, so I could just say it's the integral of 0 to 1. Within that, the PDF is just 1 everywhere. And overall, I'm just going to get 1. So I get 1. We can make a little plot of this picture. Here's my CDF. 0, 1. If I'm below 0, it's at 0. If I'm at 1, it's 1. And if I'm between there, it has a slope of x. So it's just going to connect them, just like that. And this is a valid CDF. If you go back and validate all the rules that have to be true for it to be a valid CDF, the limit at negative infinity is 0, limit at infinity is 1, it's increasing, etc. So yeah, so that's a nice example of how we can go from the PDF to the CDF. Let's look at another example of calculating probabilities using the PDF. So, example. Let's say that the PDF fx is x over 2 if x is between 0 and 2. And so it is implied, I'll write it one last time, it's implied that it is 0 everywhere else. We can plot this thing. So the kind of support of my thing is 0 to 2. If I plot f of x, it's 0. Less than 0, it's 0 bigger than 2. And then in the interval 0 to 2, it takes on this straight line. So this is the PDF now. And the slope of this line is 1/2. What do I want to do with this? Let's calculate probability. So my random variable has this PDF here. Drawing a little plot of it, and we could ask, okay, if I give you this random variable with this PDF, so the probability is distributed this way, maybe I want to say, what's the probability that I end up with a value bigger than 1? So what's the probability that x is bigger than 1? Recall, our rule is that if I want the probability that x is in some set A, I integrate my PDF over that set A. So in this case, I'm going to integrate, set is 1, scroll down a little bit, is 1 to infinity, f of t dt. So 1 is somewhere around here. And I want the area under this thing. Well, actually, I only need to care about the area up until 2 because my contribution bigger than 2 is 0. Whoops. So I could really write this as the integral from 1 to 2. And what's the formula? When I'm between 1 and 2, my formula is x over 2. Or in this case, let's say t over 2 dt. Integrate this, or you could alternatively just calculate the area of the trapezoid. What is that? That gives me t squared going from 1 to 2. No, it doesn't, right? I'm integrating t squared over 4 from 1 to 2, right? I have to bring down another 2. t squared over 4 from 1 to 2, which gives me what? If I plug in 2, I get 4 over 4, and if I plug in 1, I get 1/4. So the probability that x is bigger than 1 is 3/4. And that's believable if I look at my picture here and I look at this shaded region. It seems to be about 3/4 of that triangle. It's believable. You could do the geometry and actually show that that's true. Okay. Let's continue. Let's look at more examples. So, example. Let us have a CDF, capital F, that is, and I'm going to write it this way. It's 1 minus e to the negative x for x bigger than 0. And at 0 otherwise. So what does this thing look like? If I look at f of x against x, it's always good to kind of plot out what these things look like so you have some intuition. It's 1 minus e to the negative x is going to look something like that. We can draw it in a different color. It's going to look like that. Something like that. As x goes to infinity, e to the negative x. Oh, that's the wrong way. Let's think about this. It's going to be the other way, right? It's going to be something like, oh, it's 1 minus it. Yep, so it's, good thing we're drawing this out. Let's think about it, right? So here's my line at 1. It's probably going to look something like that, isn't it? Yeah. Is that what 1 minus e to the negative x looks like? As x gets really, really, really large, as x goes to infinity, e to the negative x goes to 0, this thing is asymptotically going to approach this line, y is equal to 1. At negative infinity, e to the negative x is going to be, close to 1. Oh no, at negative infinity at 0. At 0, it's going to be exactly e to the negative 0, which is e to the 1, or e to the 0, which is 1 minus 1 is 0. Okay, so it will look something like this. Good. Looks like a valid CDF, right? Okay. And I could ask a question, so maybe here's my question. The question might be, what is the probability that x is between 1 and 2? And I can be real sloppy about if I include a less than or equal to or greater than, or or equal to here, because this is a continuous random variable. We know it's continuous because the CDF here is continuous. And we had a theorem that said, if I wanted to calculate this probability of being in some interval, I know that the probability that x is between a and b, and here I don't have to worry about it's less than or equal to or whatever, it's continuous. I can just do this. And so in my case, the probability that x being 1 and 2 is f of 2 minus f of 1. If I know the CDF, this is a real quick way of calculating it. This will give me what? What's f of 2? It's 1 minus e to the negative 2 minus f of 1 is 1 minus e to the negative 1. And 1 minus minus 1, this just gives me e to the negative 1 minus, this is equal to e to the negative 1 minus e to the negative 2. That thing is positive, that's a valid probability. One way of solving this problem. We have this whole thing with this PDF now. Maybe we want to kind of use that way of calculating. So an alternative way of doing it is, step 1, get the PDF. So f of x is just the derivative of my CDF, which is d dx of 1 minus e to the negative x, which is should be e to the negative x. And this is going to be true as long as x is bigger than 0, right? If x is less than 0, my CDF is 0, derivative of 0 is 0. So that's good. And what do I want to calculate? I wanted to calculate this probability that we had said between x is between 1 and 2, right? Scroll back up here. Yeah, we're going to calculate probability x is between 1 and 2. And now another way to calculate that is I can say that's the integral from 1 to 2 of my newly derived PDF, right? And so how am I going to do this? This is integral from 1 to 2. And my PDF over this region is just e to the negative x dx. And so we just got a little calc 2 problem. This is negative e to the negative x evaluated from 1 to 2. At 2, we get negative e to the negative 2, minus at 1, we get negative e to the negative 1, right? And so negative negative, we can rewrite this as e to the minus 1 minus e to the minus 2, which is the probability that x is between 1 and 2. That matches up e to the minus 1 minus e to the minus 2 with the CDF way. Effectively, we've taken a derivative and then we've reintegrated, right? We took a derivative and then we calculated an integral, and so we kind of undid what we did. You're effectively doing the same kind of thing, but it shows that this works. Okay. So let's talk about what makes a valid PMF or PDF. So, theorem. PMF / PDF characterization. Okay. So, a function f is a, we're going to call it, quote, valid PMF or PDF. What we really mean by this is that, let's say there exists a random variable x with f as its PMF or PDF. That's what we really mean by valid, right? So another way to phrase this is that if I have some function f, is there a random variable with f as its PMF or PDF? And that is true if and only if some conditions hold. So we had a very analogous theorem for CDFs. We said, if these conditions hold, this thing is the CDF of some random variable. If it's the CDF, if we have a random variable and we take it CDF, these properties hold. Okay? Similar thing for PMFs and PDFs. If I have a function f, there's some random variable with this thing as its PMF or PDF. If certain conditions hold, if these conditions hold, then there's some random variable with this as PMF or PDF. Okay. So this is actually a simpler theorem than the CDF case. And there are two things that have to be true. The first one is that the function has to be positive or non-negative. It could be 0, but it cannot be negative. Okay. The second condition, we're going to break into two cases, depending if we're talking about a PMF in the discrete case, or in the continuous, we're talking about a PDF. In the discrete case, we're talking about PMF. It must be true that if I sum over all real numbers my PMF, I get 1. That is, if I sum up all the probability of being at every individual point, that's going to give me 1. And in the continuous case, the analogous fact is that if I integrate over all real numbers, I also get 1. So my PMF must sum to 1 over all values, and my PDF must integrate to 1 over all real values. So I'm not going to go through kind of a formal proof of this. I'm going to make an argument that is kind of shows why these things are reasonable conditions that must be satisfied to be a valid PMF or PDF. The kind of aside here is that, for discrete, we have that the probability are random variables in the set A as we sum over things in that set. We sum the PMF over things in that set. And for continuous random variables, if I want the probability that my random variable ends up in this set, what I do is I integrate my PDF over that set. Right? So the PMF and the corresponding PDF show up as kind of sums or integrals to calculate probabilities. We calculate probabilities by either summing or integrating the PMF or PDF. Now we know things about probabilities. These probabilities, first of all, they better be positive. Probability, whatever, is always non-negative. That was back in, say, lecture 2. So the sums and these integrals must be non-negative. And the only way that's going to happen is if the functions themselves are non-negative. If we had a negative value you could sneak in here, you could contrive an example where this integral or the sum ends up negative and you get a negative probability. That's not allowed. Okay. Similarly, note that the probability of, say, being anywhere in the whole sample space is basically the same thing as the probability that x is anywhere in the real line. And that, of course, is either the sum or the integral of the PMF or PDF over all real numbers. That thing is 1, right? So 1 is the probability of any outcome occurring. That's kind of the same thing as saying that a random variable takes on some number, right? Has to happen. So that probability is 1, and that's just the sum or integral over all real numbers. So that gives us kind of intuition for the second one. So the first one is true because the probabilities, they're used to calculate probabilities, they better be positive. And the second one is basically that, yeah, the probability it ends up anywhere has to be 1. Not really kind of formal proof, but that's kind of a sketch of what the ideas are. A more useful fact is that if I have some function, let's say g of x, okay, and g of x is always positive, we can turn g of f into a valid CDF. For example, in the continuous case, if we look at the integral of g of x dx over all real numbers. Now, it might not be 1. This g might not be a valid PMF. It might come out to be some number c, right? But it's positive. This number c is positive. If we do that, then if I define some function f as 1 over c times g, then this is a valid CDF. PDF. Why? It's positive. 1 over c is positive. G of x is always positive. The function's always positive. If I integrate this thing, right? If I integrate, for example, f of x over the real numbers, this is 1 over c. I can pull out the 1 over c by g of x, let's say dx, which is just 1 over c by c is 1. So this thing integrates over the whole real line to 1. So the class of functions that are PMFs or PDFs, you can do an analogous thing here where you replace the integral of the sum for the discrete case. But the class of functions that defines a valid PMF or PDF is not really that exclusive. It's basically, I can take any positive function, and as long as it's positive and has a finite integral, I can always turn that positive function with a finite integral into a PMF or PDF by just renormalizing by whatever the integral or sum is over all real numbers. Then that thing is kind of a valid PMF or PDF. So you'll get problems in the homework being like, okay, here's a function, there's some unknown constant, and it must, how do I choose this unknown constant so that it's a valid PMF or PDF? Well, it has to satisfy these two conditions here, right? And as long, it's usually pretty easy to check that it's positive. The other thing you have to check is that it integrates to 1. Well, how can I force it to integrate to 1? Well, I can calculate its integral and then kind of multiply by the reciprocal of whatever that value would be, and that kind of forces the thing to integrate to 1. So making a PDF or PMF, or kind of looking at the class of functions that are kind of valid PMFs or PDFs, is basically positive functions. Positive functions, and then you renormalize them in some nice way so that they integrate to 1. Okay. So the last example, before we move on to our next topic, that I want to look at here is the normal distribution. So this is a fun one to introduce. So normal distribution. So called because it's the typical one people work with. It's literally just, oh yeah, and the normal one, the one we always work with, right? So that's kind of where the name comes from. Also called the Gaussian distribution, named after Carl Friedrich Gauss, who developed a lot of the kind of basic theory of, say, regression and normal probabilities, along with other people, Dumas and people like that. The normal distribution is one I think we're all kind of passingly familiar with. So our notation here, and this is we're into our first kind of distribution with parameters. Our notation is, I can say x is distributed as n for normal, and then it has two parameters, mu, and mu is some number in R. This is called the mean, and it's some number in R. And then there's a second parameter called sigma squared, and sigma squared is called the variance. And sigma squared must be positive. So the normal distribution, I think we all kind of have a somewhat passing familiarity. It's some kind of bell-shaped distribution. So this here I'm plotting the PDF. It's a continuous random variable. It kind of has this bell-shaped distribution. The parameter mu is the mean. It tells us kind of where the bell is centered. And the parameter sigma squared, the variance, kind of tells us how wide or how fat this distribution is. How the density is spread out over the space around mu. It's a really nice model. In addition to a lot of theoretically really nice properties of this thing, it is a super nice model. It is how we think of these things. The probability is centered at some value mu and has some distribution around mu. The farther away we get from the mean, the kind of lower the density is. For near mu, it is higher density, and how much that density is spread out around mu depends on sigma squared. So you could have a case with a small sigma squared. So this is like small variance, sigma squared. Or you could have a case with a really wide sigma squared. So here's mu, and this is a large sigma squared. The density is widely spread out around mu in the large case, and kind of very tightly spread out around mu in the small sigma squared case. So it measures the variability, and we'll formalize all that in this course of the density. Okay. Let's look at a special case today. Very important special case, and this is called the standard normal. And the standard normal is when mu is 0 and sigma squared is 1. So normal 0, 1. So here, this is telling us that it is centered at 0, and it has a variance, let's say sigma squared is equal to 1. So it's kind of a very standard case, right? And looks something like this. Center is around 0, and you could calculate, say, plus a sigma minus a sigma. This is going to be approximately about 68% of the variability. If you look at plus or minus 2 sigma, then the variability, the probability of being under the curve, probability of being between plus or and minus 2 sigma is about 95% of, has a probability of being about 95%. So if you say, okay, x has a standard normal, what's the probability on between, x ends up between plus or minus 1 sigma? It's about 68%. What's the probability on between plus or minus 2 sigma? That's about 95%. This harkens back in the kind of inter-stats course why, if you want a 95% confidence interval, you typically see a plus or minus 2 sigma. Okay. This is a real fun distribution, and it's a real fun distribution to apply this theorem to. Fun maybe in a sadistic way. Fun for a math professor. So let's check that this thing is a valid PDF. Well, of course, first I have to give you the PDF. What's the PDF of this thing? The PDF of a standard normal, we'll talk about the general case later in the course, has this form. 1 over 2 pi times the exponential of negative 1/2 x squared. And this is true for all real numbers. Okay. So here, my notation, exp of x is just kind of shorthand for e to the x. So that's the function looks, of course, like this. This is e to the x, right? So my question to you, is this a valid, let's get our terminology right, probability density function? So we have a theorem, and the theorem says in order to see if this is a valid PDF, I have to check 2 things. 1, is this function bigger than or equal to 0? I think that is relatively easy to check. 1 over 2 pi is bigger than or equal to 0, and exponential of anything is bigger than or equal to 0. This exponential function is always bigger than 0. So if my x-axis is there, this function is always bigger than 0. So we're multiplying 2 things that always have to be bigger than 0. So it's going to be a positive function. The harder thing to check is the integral. We could write it to t, you could write it with x, doesn't really matter. Over all real numbers. If I integrate this bad boy over all real numbers, do I get 1? So that's kind of the problem we're going to look at. So let's look at how we tackle this integral. Okay. So what do I want to do? I want to integrate over all real numbers this function, 1 over 2 pi exponential of negative 1/2 x squared, and I want to integrate that with respect to x. And what I really want to show is that this integral better come out to be 1. Okay. So here's the trick. There's 2 tricks in this, 2 or 3 tricks in this problem. So this is definitely beyond the level I would expect you to do on homework or exam. It's really nice to see this kind of trick once. It'll harken back some flashbacks to Calc 3. Okay, here's my integral. A definite integral like this is some value. And so let's call the value I for integral. It's some number. Right? Okay? Some real number. And because f is positive, it's going to be a positive number. Okay? And so whatever the value of this thing is, I want to show that the value of this integral is 1. One way I could show that is if I is a positive real number, then I is 1 if and only if I squared is 1. All right? So we can't have a complex number, we can't have a negative number, but if I is some positive real number, if I tell you I is 1, certainly I squared is 1. If I squared is 1, it has to be that I is 1, if it's a positive real number. So these are equivalent statements. So actually what we're going to do is we're going to solve this. We're going to show that the square of this integral is 1. So what is the square of this integral? Well, what's the square of any number? I just multiply them, right? So my first number, I, is this integral, right? That's I. And then I'm going to multiply by I again. So I'm going to rewrite this integral. That's some value, this thing, some definite integral, it's just a real number. And I'm going to multiply by this again. So I'm going to say, again, it's multiplied by the same integral. 1 over 2 pi. But I'm going to change my variable in my integral. I'm allowed to do that. In fact, I could change it to be another variable, y. It doesn't matter. The variable in the integral is called a dummy variable, right? It doesn't mean anything. It's just for our own kind of psychological evaluation of these things. But it actually is not a meaningful concept. I could place it with t or z or a, b, or c, right? As I did above, I had the integral with respect to t, right? This is kind of meaningless. So I'm allowed to say it's integral with respect to y. But now I have the multiplication of two integrals. And Calc 3 says, so let's justify this step with the notation of Calc 3. And Calc 3 says I can actually write this as an iterated integral. That this is the integral with respect to dx and then dy. So I can combine them. Because they're kind of different variables, I can smush them together. And I could write this as this iterated integral in this way. And so I'm just going to multiply the two functions. 1 over root 2 pi times 1 over root 2 pi. I can get rid of the square root. I can just write this as 1 over 2 pi. And then what do I have? I have exponential negative 1/2 x squared, and the exponential, let's move this over, but of negative 1/2 y squared. And dx dy, doesn't matter the order. And I can actually use some rules. I'm just going to write this as the integral over R2. I'm going to be lazy and not write a bunch of double integrals. I can use some rules of exponentiation and say that I can combine these exponents, right? The multiplication of two exponents is the exponent of their sum. So this goes into negative 1/2 x squared plus y squared. Dx dy. Okay, I've just made the problem a lot more complicated, it seems. But I'm not done. There's more. So let's make this more complicated until we see the nice trick at the end. So what's your worst nightmare from Calc 3? The worst nightmare, of course, is polar coordinates. So let's just make this more complicated by introducing some polar coordinates. Okay. Real quick review of polar coordinates from Calc 3, right? So normally we work in what are called Cartesian coordinates. So I would have some point here, x comma y, right? I could alternatively relate this, denote this point in what are called polar coordinates, where I have some angle theta and some radius r. So I could write this as the polar coordinates r theta. And there's a relationship where I can transform back and forth between polar coordinates and Cartesian coordinates. And that's just basic trigonometry, right? So in this case, x is going to be r cosine of theta. Y is going to be r sine of theta. If I look at x squared plus y squared, this is going to be r squared. So that's some more rules of trigonometry. X squared plus y squared shows up. And because you're doing calculus, we then have to justify that we can swap out dx dy. Anyone remember? It's r dr d theta. So real quick justification for that. Normally you do integration with respect to Cartesian coordinates, so you're thinking about some infinitesimal dx and some infinitesimal dy, right? So you're integrating with the squares dx by dy. Very hand wavy, right? Okay. Alternatively, now we're in Cartesian, we're kind of integrating across parts of pi slices, right? So we're going to integrate across this pi slice. And this pi slice is dr on this direction. It has an angle d theta, and so this side of it is by the rule for arc length. It should be r d theta, right? So if this side here is r, then we have a dr added on, then this should be approximately r d theta. That's just angle times radius gives you arc length. So the area, in a really hand-wavy way, is r d theta times dr, or r dr d theta, right? That's really hand-wavy. We could actually maybe justify that later in this course, or in a kind of analysis course. You'd really rigorously justify that. But okay, 30-second review of polar coordinates. Okay, we're trying to solve this integral, right? And this bad boy can fit so many polar coordinates. So let's rewrite this, but using what we know about polar coordinates to change it from an integral, a Cartesian integral, to a polar coordinate integral. Let me just rewrite the integral here. So the integral is, let's pull out my 1 over 2 pi. And then before I was doing this double integral of what? exp of -1/2 x squared plus y squared dx dy. Right? That was my integral. Just check real quick. Yep. Now I'm going to substitute in. Oops, I need my 1 over 2 pi still. Okay. Substitute in. exp -1/2 x squared and y squared, I can replace with r squared. And dx dy I can replace with r dr d theta. My limits of integration before were kind of 0 to infinity in the x and 0 to infinity on the y. But now my limits of integration, first we're going to do with respect to r. R can go as any positive number, 0 to infinity, and theta can go any angle, 0 to 2 pi. So that's my integral. 0 to 2 pi theta, 0 to infinity of r exp -1/2 r squared. This is an integral we actually know how to solve. Here is a Calc 2 trick, which is called a U Substitution Trick. Let U be 1/2 r squared. Du is nicely just r dr, right? R dr shows up here. 1/2 r squared shows up there. U substitution trick says I can write this as 1 over 2 pi. I'm gonna kind of leave off my limits for now. Let's just first look at the inner integral here, right? So just the r integral. So this is 0 to infinity exp -1/2 r squared r dr. With respect to u, I can now replace this as e to the negative u du. And that's a super simple integral. This is just negative e to the negative u. If I kind of leave off my limits here, or if I want to put on my limits, so let's just come down here. So this integral should be, I can place back in u, e to the negative, what was u, is r squared, 1/2 r squared. And my limits were 0 to infinity. And so what do I get? At 0, at infinity, let's do the top one first, right? At infinity, this thing basically goes to 0. Because it's e to the negative value. Again, bigger, 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 bigger negative value. It's a 1 over e to some large value. This thing goes to 0. Subtract off, at 0, it's just 1. But it's minus 1, because we have this minus sign up front here. So I get 1. Well, that's nice. So my original integral, let's pull this down in red here. Now, 1 over 2 pi, integral 0 to 2 pi. That inner integral with respect to r, that's just 1. And I'm just left with the d theta. And of course, if I do that integral, it's 1 over 2 pi. Integral 1, 0 to 2 pi, d theta, 2 pi. It's 1. And so way back, if I go back up, what was this whole thing equal to the beginning? This whole thing was equal to I squared. So what I've shown is that this I squared is 1. Hence, my integral is 1. So my theorem is true, or my PDF is valid, right? So I showed that this second part. I showed that this thing, which I was calling I, is 1. That integral is 1. The normal PDF is valid. So the normal distribution is a gorgeous distribution kind of from practical use. It's a little tricky sometimes from the point of view of actually doing calculus on it, because it has this weird exponential of a square. So you saw on this trick, which is kind of just a nice little trick to see once in your life. The machinations you have to go through to kind of prove facts about it. We'll see similar tricks throughout the course. It's a little beyond the scope of what you're going to be expected to do on homework or exam, because that's thinking of going to polar coordinates, multiplying it. Yeah, it's a little kind of beyond the scope. But that's an example, fairly complicated example of that theorem in action. Okay, so the last topic, or the next topic, as we start to get into the real fun stuff in this course, kind of move away from counting into what feels like more like a calculus course now. Our next topic is expected value. So let's introduce this topic kind of at the end of the lecture today here. Expected value. Incredibly important topic. So let's first talk about, let's just give a definition of what the expected value is. If x is a random variable, then the mean, or also called the expected value of x, and our notation, we're going to denote the expected value of x as e of x, or sometimes people use mu, or mean, of the random variable, is defined as, we need two cases. I haven't talked about whether or not this random variable is discrete or continuous yet. So we're going to have two cases. One is if our random variable is discrete. You'll see this a lot in this course where we have two cases for discrete and continuous. If we have a discrete random variable, then e of x, that is our expected value of this random variable, is defined as the sum of x times f of x over all the real line, or alternatively over all the support. You could alternatively write this as x in the support, because if we're not in the support, little f, that's the PMF here, would be 0. So either way you can think about it. The first one is kind of the formal definition, but really you can ignore points where PMF is 0. So what is this? This is the sum of the values times the probability of seeing the values. So it's basically like a mean or a weighted sum of, so let's just write this out here real quick. This thing is a weighted sum of values x can attain, weighted by the probability we see them. It's basically, so again, it's basically a kind of average, a weighted average of all the possible values we could get for x, weighted by how likely is it we see each of these values. In the continuous case here, maybe not surprisingly, the expected value of a random variable is, well, we're going to replace the sum with an integral. It's going to be the integral over the real line of x times f of x dx. So that's the definition. In the discrete case, you sum x times f of x over all the possible values. And in the continuous case, you integrate x times f of x over all possible values. So let's just kind of talk a little bit about what this looks like. Okay. So one way to interpretation is that the expected value of x is like the balancing point of distribution of x. So, for example, if we looked at the discrete case, you could imagine plotting, say, the PMF. We have this kind of stick plot, right? And there are different kind of masses, and you can imagine these masses kind of aligned on this bar like this. And if you were to kind of put a fulcrum to balance them, the point to hold this, point to balance the PMF is the mean, mu, which is the expected value of x. And in the continuous case, you could think about it the same way. In the continuous, again, you have kind of this continuity of density, and again, you could kind of imagine, okay, there's some balancing point. Probably not over this hump, because then you have too much over here. Probably somewhere like here. You know, I don't really know, but the balancing point here again is what we're calling the expected value, or the mean, mu. Either e of x or mu, that's fine. So kind of the point where you balance the distribution. Again, in the discrete case, and let's just draw a little divider here. In the discrete case, so if I have discrete random variable on, let's say on some values, x1, 2, 3, etc., the expected value of x, so this is my support. That is, this is the place where the probability of finding x is not 0. Then the expected value here is x1 times the probability. We land at x1 plus x2 times the probability. We land at x2 plus x3 times the probability. We land at x3. And so it's basically this sum, or kind of average, of the different possible values, x1, x2, and x3, weighted by how likely is it that we're x1 or x2 or x3. And you can think about it in a similar way if, for the continuous case here, this is the integral of x fx dx, right? And so it's basically the value multiplied by the density. And we kind of sum or integrate that up. So this is the kind of super important idea of expected value. And we'll see some examples of how to calculate next time, but it is at the end of the day just what we refer to as the mean of a distribution or a random variable, or the value we kind of expect in some ways for it to take on. It's a typical value. It's the expected value. And it's somehow kind of the weighted average of all possible values. In the discrete case, it is exactly some kind of weighted average by the probabilities. And the continuous case is kind of the continuous analog. Okay, so we're going to stop there for today. And next time we're going to pick up with expectation and look at some examples.